You know the drill. Differentiation by first principles. Let's go through and start talking about it. So last lesson, we talked about IROC, instantaneous rate of change, and the really important statement from last lesson was that whilst you can calculate approximations of the instantaneous rates of change in many ways, and the textbook outlines some of those, and we've talked about some of those, the best way by far is to get a line segment that's close to the point that you want to find the rate of change for, and another coordinate, so get that point and another coordinate to make a line segment, and then create your rate of change from that. And that line segment is called a secant, by the way, which is the language used in your textbook as well. Sorry? How do you spell secant? Secant, S-E-C-A-N-T. So you can see one there. That blue line segment is a secant. Calculate the IROC accurately. Let's take the function f of x equals x squared and determine the gradient between x equals 1 and x equals 2. So we can do that fairly easily. And I'm going to do that just quickly on here. There's my first coordinate. There's my second coordinate. I'm going to find the gradient of that blue line. And hopefully you can see that whilst this line segment is fairly big, the gradient of that blue line is going to be a fairly accurate representation of the gradient of the red line at most of those points in that line segment. So that's pretty good. We can do that gradient fairly easily. The gradient m is equal to y2 minus y1 over x2 minus x1, which is equal to, this coordinate here is 1, 1, because the function is y equals x squared, and 1 squared is 1. This coordinate is 2, 4, because 2 squared is 4. So we get 4 minus 1 over 2 minus 1, which is equal to 3 over 1, which is just equal to 3. So the gradient of that blue line is 3. It looks pretty steep. The scale's not perfect. You can see that I go along 1, I go up 2 in the same scale. So it's not a perfect scale, so it's hard to visualise that, how it looks. But the gradient's definitely 3. Any questions on that? Now we're going to do a little bit like what we did last lesson. We're going to determine the gradient between 1.9 and 2. This will give us a better estimation of the gradient at 2. And that's the point of this process. So again, I'll mark the 2 points on here. I haven't drawn the line segment because you'll see it's pretty much on the red line. This is 1.9, and what's 1.9 squared? Anybody know off the top of their head? That might come up. That would only be in a tech active exam, obviously. So there's my gradient for this one, is m equals y2 minus y1 over x2 minus x1, which is 4 minus 3.61 over 2 minus 1.9, which is 0.39 over 0.1, which is 3.9. So the gradient was 3, now it's 3.9. You see that's moved up. What do we suspect the gradient is at that point x equals 2? 4. We expect it's 4. We suspect it's 4. We're heading, because we're basically doing limiting here on this initial process, and we expect that we're heading towards 4. Determine the gradient between 2 and 2 plus h. So this is where it becomes abstract. And we're going to generate an understanding of what's going on by creating an h value, where before we were choosing points that are really close. Now I'm going to choose a point h, and then we're going to consider what happens as h gets really, really small. And that will be our differentiation by first principles. So here's my point 2, and 2 is 2, 4. And 2 plus h, I'm just going to put it up here. It's a fair way up, but it just makes my diagram more clear. So I get 2 plus h. What's the y value when the x value is 2 plus h?
2 plus h squared.
2 plus h squared, good. And I'll leave it like that for now, but that's what the y value is. If I wanted to determine the gradient between these 2 points, then the gradient m is still equal to y2 minus y1 over x2 minus x1. And in this case, that's 2 plus h squared minus 4 over 2 plus h minus 2. And I'm going to simplify this down. I'll expand the bracket, so I get 4 plus 4h plus h squared minus 4 over h. And the 4's cancel out, and I get 4h plus h, no I don't, oh yeah I do, yep, over h, that's a 4. and that's equal to 4 plus h. Yeah? Now, here's something interesting. What happens to 4 plus h as h gets really small?
Gradient smaller.
Sorry?
The gradient gets smaller, yeah.
It does get smaller, and what does it go towards?
4.
4. So, like, if h is 0.1, that's not that small, and we're going to gradient 4.1. That's pretty boring. If h is 0.01, we get 4.01. If h is 1,000 zeros and then a 1, we get basically 4, don't we? So if we wanted to find the gradient, and you've done this a couple of lessons now, if we want to find the gradient at 2, we do it by creating a line segment between 2, 4 and some point really close to 2, 4. And in this case, I'm saying let's do it algebraically and consider h is a really small value. It's just above 2, and so it's really infinitely close to 2. And the algebra works. This simplifies down to 4 plus h quite nicely. And if h is really small, we get a gradient of 4. So therefore, based on our idea of limiting, the gradient at 2 is 4. And we can't technically ever find the gradient at 2 because we can't use the same point to find a gradient. But if the gradient just before 2, well, with a line segment of 2 and just before 2 is 3.999999, and the gradient of a line segment from 4 to just above is 4.000001, well, the gradient at 2 is 4. Yeah? That's the mathematical principle that we're going to cover today.
Just make h 0?
Well, you could do, but then up here, all of this is wrong because we divided by 0.
Right, yeah.
Which is, and think about it like this, if you got asked, like way back in year 8, year 9, when you're first doing gradient, and Miss B4 said, calculate the gradient between 2, 4 and 2, 4,
Yeah.
then that would happen. You'd have a problem. You'd actually end up with 0 divided by 0. And then that, that's nothing and everything and a world of pain. Okay. Good question. Any other questions? So we've gone for, and I'm pretty comfortable, last lesson today, that before I introduced h, every single person in this room was on board and very happy with the idea of just, make it smaller and smaller, we're getting better. Oh, look, it's going towards this number, magic. Okay, I've introduced h, which some of you might not be quite as happy with that now, but I'm telling you right now that this is a very complex process I'm going to teach you the formalities of now, differentiation by first principles, that people find really hard, but that's it, just there. It is the thing that you are comfortable with an h added to it. So it's not actually that bad. So I'm going to tell you that and promise you that. So what happens if we make h really small? The answer is m becomes 4 plus something really small. That's quite mathematical. And that just equals 4. So, determine the IROC of f of x equals 2x squared plus 7x at x equals 3. Should we do this again with an h argument? I'm going to introduce the limiting process a little bit later today, but I'm going to do this with an h argument to start with. So, I've got f of x equals 2x squared plus 7x at x equals 3. A really rough diagram, an inaccurate diagram just to show you where we're heading. It's a quadratic, it might look like that, it might be in a different quadrant, I don't really know. But it's a quadratic, and at x equals 3 we've got that point there. What we need to know is what is this coordinate, and then we'll have another coordinate which is 3 plus h something. And then we can find the gradient. So I need to determine that coordinate. So I'm going to start by determining the coordinates I'll use. Coordinate 1 will be 3, something, and that something will be f of 3. So remember our function notation. So we need to find the coordinate of that point. The y value is 2 times 3 squared plus 7 times 3. 2 times 3 squared is 9, 18 plus 21 is 39. So this is 3, 39. That's our first coordinate. Our second coordinate is harder and easier at the same time. It's just 3, so it's not just 3. 3 plus h, 2 2 times 3 plus h squared plus 7 times 3 plus h. Now I chose this example deliberately because it looks like in the previous example everything worked out. The h was on the bottom, there was only h factors on top, we could cancel out, great. This is a lot more complex and there's no guarantee that everything's just going to work out this time. And I'm going to prove to you that it always will for a polynomial function. Later on we'll do periodic exponential. It doesn't all just work out there, it's a bit harder. But here, for polynomial functions, it will just work out. So I'll show you that now. There's coordinate 2, and my gradient m is equal to, because I've got f of x here, I'm going to change the notation. I'm going to say f of x plus h minus f of x, so this is the other notation, over x plus h minus x. Now that denominator is magic. It's always x plus h minus x, because we're always dealing with the x value and then the something plus h. In our case, I'm definitely going to run out of room here. In our case, we've got f of 3 plus x, so x equals 3 for what we're working with. We get 2 times 3 plus h squared minus 7 times 3 plus h, and then that is subtract y2, which is 39, and that's all over 3 plus h minus 3. And so simplifying this, I get 2 times 3 plus h squared. It'd be really handy for you to be able to expand binomials quite quickly. 3 plus h squared becomes 3 squared, which is 9, plus 2 times 3 times h, which is 6h, plus h squared. So we went through those easy expansions, practiced them. Some of them I think are on your formula sheet as well. Minus 21 minus 7h. The negative 7 carries through to both of these things, so it's negative 7 times 3 and negative 7 times h. That's a negative, and that's a pretty common problem. Minus 39 all over h, because the 3's cancelled out again and always will. And then I get 18 plus 12h plus 2h squared minus 7h. Minus 21 and minus 39 becomes minus 60 all over h. Does it become minus 60? What's the... Oh, yeah. Oh, look at that. That's plus. That's plus, everybody. Look, there was a plus there. Sorry. Far out. Having a shocker. There we go. Plus. That means that's plus. That's plus, and this becomes minus 18. Which is nice. Can you tell me why I knew I had a problem then? So I'm expecting to get to a point where h will cancel with things that only have h factors. And I was going to end up with a number. So I know that 18 should cancel out. And I saw this is an issue. Now I've got this. 12h, let's change that to 19h plus 2h squared over h. I can cancel an h out of each. If you need to, factorise the numerator, that's fine as well. And I get 19 plus 2h. Now, what happens to 19 plus 2h as h gets really small?
It gets closer to 21.
Gets closer to 19.
Oh, wait. No.
If we talk about the limit as h approaches 1, this will get closer to 21. If we talk about h getting really small, it means it's approaching 0, so it gets closer to 19. So therefore, as h gets really small, m approaches 19. Any questions? If h is really small, I can see a couple of people looking at me a bit confused. But as h is really small, if h is 0.1, then we've got 19.1. If h is 0.001, we've got 19.001. Never technically reaches 19, but it gets really, really, really close the smaller we make h. And we know that the closer we get those 2 points together, the more accurate a gradient that we'll get. Are there any other questions on that? stuff. This is 80% of the formal way of doing differentiation by first principles. I'll show you the other 20% a bit later in the lesson. We're up to notation. Yeah, there's the next bit, but I'm going to show you that a little bit later because that's in exercise 18B. But for now, I'm going to give you some time to do exercise 18A. So looking around, I don't see anybody I'm going to upset if I move up. So with that in mind, I'm going to move up to here. 18A, there's a couple of questions. It's 9:27. I'll get back to you at about 9:55. How about that? And we'll do the second part. Cool. Thanks.